so this is 2.1, day 2. We're still talking about rates of change and limits. Okay? All right, let's go on to talk about that. So, there are some properties. The book calls it a theorem. Okay? These are rules that have all been proven. But the first one is this. You need to know that if you see LIM, x goes to something of A, the answer to this is just going to be A. Okay, so we're talking about constant values, where A is a constant. Let me show you an example of this. This is very simple to understand. Let's say you're given LIM, x goes to 10 of 5, and you're asked to find that limit. Okay, well, where's the function? Well, the function is right here after the lim. This is your function. So we're talking about f of x equals 5. That's a very simple function. Can you guys show me with your pencil what f of x equals 5 looks like? What does that look like? Yeah, this is horizontal line, right? Okay, so we're talking about a horizontal line. Like that. And we're talking about the region where x is near 10. So that's over here. This is 10. And what the limit means, remember, is this. What is the y value of this curve when you are near x equals 10? So if you approach x equals 10, what does the blue or the green curve approach in the y direction, in the sense of y? Well, I mean, you can zoom in all day on this region of the graph right here. You're going to find that all the y values are 5 in this region, right? Whether you're near 10 or at 10, the y values are 5, all of them. So it's no wonder the answer to this limit is 5. See? So this brings up an interesting point. What if it had been limit as x goes to 100? What would the answer have been? 5. What if it was pi? 5. What if it was negative 2 million? Pi. Yeah. So the limit of a constant is just that constant. That's the first rule. The next time you just blaze right through that. Don't even have to think about it. And then number 2, the rule is if you have LIM x goes to c of x, this is just going to come out to c. Okay, so let me explain that one. All right, so the example that I'm going to pick is LIM x goes to 10 x. Okay, so if you just take the rule very literally, right? Let's see. The rule is saying limit of x as x goes to c is c. Well, this is that exact situation. We've got limit of x as x goes to 10. So it's supposed to be c. C is that number. So the answer is 10, right? The answer is 10. Okay, so why is the answer 10? Well, where's our function? X is our function, right? Y equals x is our function. Show me with your pencil what y equals x looks like as a graph. Yeah, you're all holding your pencil the right way. It's that 45-degree line, right? Okay, so we're going to have y equals x this time. Looks like that. And we happen to be out at x equals 10. But if you're anywhere near x equals 10, what's the y? 10. That's right. Because y is equal to x. Okay, so I'm reluctant to draw a point at 10:10. I don't want to draw a point at 10:10. Because if I draw a point at 10:10, then we're missing the point. I'm serious. Because if I plot the point 10:10, then we're not understanding what the question's asking. We're not asking what's at 10. We're asking what's near 10. So from for me to plot a point at 10, 10 would be sort of to display that I'm talking about 10, 10. I'm not. I'm talking about the region near 10. If you're at 9.9, the y is 9.9. And if you're at 9.99, the y is 9.99. See? And if you're at 10.1, the y is 10.1. If you're at 10.01, the y is 10.01. All of the numbers, all of the y values near x equals 10 are near 10 as well. But I want to talk about 10, 10. Because limits are not a question of location, they're a question of destination. So you're approaching 10, but you never talk about 10. That is really important. Unless they ask you for f of 10, that's different. But we're not asking for f of 10. All right, so some students get really too comfortable with limits, and what they do is they just ask, oh, what would happen if I just plug 10 into here? And they get the answer. And that works on so many problems, but they don't understand what it means. So if you want to just plug this in next time, that'll work great. But understand that we're not talking about point 10, 10. We're talking about its neighborhood. All right, let's go on to the third rule. So the third rule and the fourth rule kind of go together. But the third rule is saying this: LIM as x goes to a number of f of x plus g of x is LIM of f of x plus LIM of g of x. So one way to say this in words would be that the limit of a sum is the sum of the limits. That would be a way to sort of abbreviate that into a sentence, and it's kind of catchy. You can say that with a lot of these rules. The limit of a constant is just that constant. The limit as you go to x is just that limit value. The limit of a sum is the sum of the limits. This also works with differences, so you can just change it to a minus, and that's rule 4. Okay? Rule 5 talks about multiplication. Rule 5 says this: the limit of f of x times g of x is the same as the limit, should be a c, at f of x times the limit of g of x. Okay? So this is allowing us to say that the limit of a product is the product of two limits. Okay, there is a rule about this you have to be careful with. Let's say you did this on a certain problem, right? And let's say that this was like x. And let's say that this is like sine of 1 over x. Kind of like that problem we did in number 71. Okay? You actually wouldn't be allowed to do this in all cases because it wouldn't give you anything meaningful. So this is really weird, but this rule is allowed when it works. And that sounds strange, but this rule is only allowed if it works. If you do something like this and you find yourself getting a strange answer that's not meaningful, like undefined or something like that, okay, or no limit, that's another thing we can talk about, then you shouldn't have done this. It's kind of like quantum reality. It's like the particle isn't there until you observe it. Listen, the rule isn't valid unless it works. So if you try something like this and you get nonsense, you got to go back to the drawing board and try something else. You'll see that when we do our examples in a minute. Okay? I know it sounds really mystical, but it's very true. So the way the book says it is, as long as the limits exist, this rule is valid. Okay, we could write your sentence there. The limit of a product is the product of the limits, right? Limit of a product is the product of the limits, or the product of the factors, limits of the factors, right? Okay, how far can we extend that logic? Well, we can actually do division also, but before we do division, let's talk about a special case of multiplication. So what would happen if you had, for your f of x, it was just like k. That's just a number. So k is a constant. And I don't know why I chose g of x, but it could be g of x or f of x, doesn't matter. If you're dealing with a situation like this, you can actually use rule 5 to split it into this. I just exercised my freedom to use rule 5, right? I split it up. And according to rule 2, this comes out to k, this first limit. The limit as x goes to c of k is k. So according to rule 2, we can abbreviate it like this. So how would you write a sentence for this one? Well, you could write something like the limit of the product between a constant and a function is that constant times the limit of that function. Or you can just simply say you can factor out a coefficient. Because that's kind of what I ended up doing, right? I just took that k, and because it was just a number, I popped it out front. Okay, so I'm just going to write you can factor out a coefficient. Coefficients factor out. That is a really important rule. And if for some reason you don't like it out front, put it back in. You can pull the k out or put the k back in. It's up to you. All right. That's actually a special case of rule 5. Let's go to rule 7, which is the quotient, the division. Okay, so rule 7. What happens if you have a fraction, which happens all the time, any rational function looks like this. If you're dealing with this situation, my question is, are we allowed to split it into two limits? Can I just do this for the numerator, and then the same thing on the bottom? LIM x goes to c g of x. And the answer is yes, if it works. Okay, so if this leads you down the road to something like infinity over 0 or something weird, then I suppose that wasn't a very good idea. So we'll use it if we need it, but only if it seems to work. Also, if it gives us like 0 over 0, that means we kind of failed. The question is done in this way. Again, you'll see in a second with an example why this might not always work. Okay, let me say one more thing about this. There's also something else that has to be true about this original problem. What do you know about g of x? Since it's on the bottom, there's something it cannot be. 0, right? So I don't know why they would give you a problem where g of x was 0, but they probably shouldn't, right? There's one exception. If both f of x is 0 and g of x is 0 at a certain value of x, then this problem can actually be done. But for now, just remember, g cannot be 0, that's obvious. And these have to be meaningful in the end, otherwise you're wasting your time. I have to do one more rule and then I can show you some examples. The last one is rule 8. Oh, so that last one would be the limit of a quotient is a quotient of the limits. So I'm abbreviating now. I'm being lazy. Okay, rule 8. This is one of my favorite ones. This rule is very powerful. No pun intended. No, it really will help you later. It's one of my favorites. So, let's say that you're doing a limit of a function and there's this annoying power on the function. Okay, so this might be like x squared plus 15, and that might be like 45th power. Okay? So you're dealing with an ugly function and it's got power on it. Well, we can actually do the limit first and then do the power. So we can bring the lim inside the parentheses with the f of x and make it look like this. And save the power for last. I'm telling you, this rule will save you on some really hard problems, okay? It's very, very important, this rule. Okay, so the limit of a function with power is the power of that function's limit. Something like that, maybe. I want to do that. Write that sentence. What kinds of powers? Well, positive numbers. Square, third power, fifth power, 100th power. Okay?
What about 1/5?
What?
1/5?
1/5? Is that what you're asking?
Yeah.
Yes. It works for fractional powers, rational powers, like 3/4. That's where this rule gets really helpful. Let's say you're talking about a problem that has a square root in it, right? So let's say you're trying to figure out something about this. Let's say you're actually going to 0. By the way, I like to call limit as x goes to 0, I call that limo. You know, like long black car? I call them limo, because we use it a lot, especially with definition of derivative. We'll say, I'll just say limo, okay? But let's say you're trying to do this problem. This is an ugly problem. This is a really ugly problem. But remember, we're saying that we can save the power for last, and we're dealing with a half power. In other words, we can do the limit of the inside first. And if I'm not mistaken, we memorized this yesterday. What was the limit of, the limo of sine x over x? 1. Right. So that rule is very powerful. Maybe the pun is intended. I don't know. This allows me to also talk about reciprocal problems, because technically reciprocal means -1 power. Watch this. Let's say you're trying to do this problem. X over sine x. Yuck. Well, I happen to remember sine x over x has a limo of 1. We talked about that yesterday. You're supposed to memorize it. Maybe I can make that work to my favor. How about we write this as limo sine x over x to the -1 power. Same thing. Rule 8 allows me to do the limit first and then the power later. Beautiful. And I get 1 to the -1, which is just 1, because 1 to any power is 1. That rule will save us a lot of like weird proofs and stuff. Rule 8 will give you a lot of flexibility. Okay. Both of these examples that I just did require you to know that the limo of sine x over x is 1. But I asked you to memorize that yesterday, right? So I was actually looking for a chance to use that. Okay, now let's go and just look at some problems. By way of example, I've already done a couple of examples there. Can't resist when I'm writing rules to throw in some examples. But let's say you're asked to find this. And let's do this more meaningfully. Let's not use C anymore. Let's actually put a number in. We're in example phase here. So let's use a 5. I like 5s a lot. Okay, so how would you do this problem? Well, I'm not going to lie to you. You can plug 5 in right now. The answer is going to give you 26, right? Okay, I'm not going to lie to you. That's the answer to this problem. But I want to show you why that's the answer. So the first thing I'm going to do is split it according to rule 3 and rule 4. I'm allowed to split this into 3 limits. So the first one is lim x goes to 5 of x squared. The second one is lim x goes to 5 x. The third one is more of a subtraction thing, but rule 4 allows it. So I made this into lim x squared plus lim x minus lim 4. And I forgot to write my little 5 there. Okay. All of these can be solved by using a rule or combination of rules. For example, this first one, there it is, the limit of a function with power on it. How about we do the limit of x first and save the power for later. The second one, I'll do that one in a minute when I do the first one. Okay, what about this third one here? What is the limit of a constant? Look at rule 1.
Constant.
Yeah, so does it come out to 5 or 4? It comes out to 4. Okay, good. You guys were listening to rule 1 there. That's rule 1. Rule 2 will help me solve the lim as x goes to I of x. So what does rule 2 say about lim of x goes to c of x? Comes out to c, right? So what does this come out to? 5. 5, and this comes out to 5. That's according to rule 2. So, like I said, the answer is 26. You're getting 5 squared plus 5 minus 4. I'm not trying to stifle you. I'm not trying to slow you down. I'm saying that the reason you can just start this problem off by plugging in 5 is because of my whole proof here. Okay? Just be aware of what you are allowed to do, but don't take it for granted. Somebody has proven that it's okay to do some certain things. Next time, use it. Maybe on the homework, you could do a couple things like I did like that, just to remind yourself that the rules are allowing it. It's not, don't take it for granted. For example, if this had been this symbol right here up front, if that had been a derivative symbol, we could do this. If it had been an integral symbol, we could do this splitting. If it's a sigma, you know, these capital sigma things, you're allowed to do this splitting. Okay? But there are symbols in math where you're not allowed to do this sort of thing, split it into parts. So we just have to be cognizant of that. All right, let's go to another example. How about lim as x goes to 5, x squared times x minus 2. So the first thing I see is that this is a product. Right? This is like f of x times g of x is the way it looks to me, right? It's two things, two functions. So I'm going to start this off by splitting it into lim x goes to 5 x squared, and separately lim x goes to 5 of x minus 2. Okay? And then we can write lim x goes to 5 of x, save the square for last. Okay? And we can do rule 4 to split this into lim 5 of x minus lim 5 of 2. Okay, and we already talked about this a minute ago. This is 5 squared, and this is 5 minus 2. So this comes out to 75, which is the same thing you would have gotten if you just plugged it in the first place. But I'm saying again, one more time. If you plug it in, you get the feeling like we're talking about f of 5. We're not. We're talking about the region here in x equals 5. So I'm just warning you not to over-trivialize calculus. Okay. Let's do another example. Remember I said that rule 5 and rule 7 are only allowed if they work? That was a really weird thing for me to say, but I'm going to show you exactly what I mean by that in our next example. And then you'll agree with me. Okay, so let's say you're given a problem like this one, and it says find the limo of tan x over x. Okay, so my first thought, if I see this problem, is going to be, hey, a quotient. I'm going to put limo tan x over limo x. So let's see if we can exercise rule 7. Can I exercise rule 7? Let's see. Limo tan x and limo x. Well, this is all fine and good, except when it comes time to find these limits, I'm going to get 0 over 0. Okay? The tan x thing, you're going to have to just consult your table on your calculator, and you'll see that anywhere where x is near 0, y is also near 0. So this actually comes out to 0 on top. And this is, according to rule 2, this comes out to 0. So we're getting 0 over 0 on this. And what did we say yesterday about 0 over 0? Yeah, it's not 1, it's not 0, it's undefined. So what does this mean?
It's a weird answer.
It's a weird answer, which means I should not have used what? Correct. I should not have used rule 7. But I didn't know that at the time. I tried it first and I realized, oh my gosh, this isn't working out. I'm getting undefined. Okay, so this is undefined. So rule 7 was the wrong rule, see? Back to the drawing board. Sometimes you don't know until you try. So what do I do now? Huh? When you solve limit problems, there's no one way to do them. This is what frustrates students on limit problems. Let's see, yesterday we did an example where we factored the top and we're able to reduce it. I don't think that's going to happen here. Didn't we memorize a special limit yesterday? What did I ask you to memorize yesterday? I only asked you to memorize one thing. Sin x over x has a limo of 1. Okay. Can we use that to our advantage? Separate tan into what? Sin x over cosine x? That might be a great idea. So let's try that. Okay? So trig substitution. Let's see what happens. That's called a trig substitution when you use an identity to replace something. So let's look at tan x as sin x over cos x. I think this is going to give us an answer. This is good news. Okay, so I just have to figure out how I can split it. I wasn't allowed to use that quotient idea. Maybe I can write this as sin x times secant x over x, right? After all, 1 over cosine is the same thing as secant. Right? And then instead of thinking of this as a ratio, I'm starting to see it more as a product. I'm starting to see it as sin x over x times secant x. See that? This is all very intentional. So let's see what we got now. I'm going to split this according to rule 5 into limo sin x over x times limo sec x. The first limit I had you memorize yesterday. So it still is without proof, but it is simply 1. And this other one, maybe you remember the graph of secant. I have it up on the wall here. Secant is basically that graph that bumps off the top of cosine, remember? So cosine is that wave, and then secant, you've got these little upside down and right side up parabolas attached to the peaks and valleys. You guys remember this graph, secant? Yeah. Okay, so if you're anywhere near 0 on the secant graph, it's actually at 1. Or if you don't believe me, you can write this as cosine to the minus 1. I'm going to erase this in a minute, so don't write it. But you can write this as cosine of x to the minus 1 power. And then you can bring the lim symbol inside and save the power for later. And then just ask, do I know limo of cosine? Well, yeah, anywhere near 0, cosine is going to come out to be 1, right? Okay, so I think you should know the secant graph pretty well by now to know that near 0, it comes out to 1, and the answer is 1. Now, why is the answer 1 to this problem? Is it because 0 over 0 is 1? No. Do you think a student might actually get this problem right? Because they did this, and then they put 0 over 0, and then they concluded that that's 1, and so they were like, I got it right? That might happen, right? On my test, the student might actually do this problem like this and misinterpret this to mean uno. Should I give them the point? No. I can't. Because they fell for the trap of splitting it into a quotient, and that doesn't work. And they misinterpreted 0 over 0 as 1. Okay. All right, let me say one more thing about 0 over 0. Technically, it's not undefined, it's indeterminate. Okay? So what that means is, indeterminate means we don't really know what's going to come come out of this problem. If you ever get 0 over 0 when you're doing a limit, chances are there is actually an answer. You just went about it the wrong way. I've seen problems where my first effort gave me 0 over 0, but the final answer was 15 when it was done properly. See what I'm saying? So we don't know what this really means in the end because it was a bad start. Just a failed test. That trig substitution was a good thought. Who came up with that? Hunter. Okay, good. All right. Let's just talk about left and right limits real quick. This is not difficult. Unless limits are brand new to you, then this might sound a little weird. But if you ever see a plus or a minus superscript, like in this case, let's say you see a problem like this, LIM, and then instead of x goes to c, there's a little plus right there. Has anyone ever seen that? Okay, this is basically called the limit, this is how you say it, the limit of f of x as x approaches c, and you don't say c plus, you say c from the right, is how you say it. You say c from the right. So I'll write it out for you. Limit of x, the limit of f of x as x approaches c from the right. That's how it's pronounced. So please don't say c plus. Say c from the right. Okay? And the same thing if you see the minus, that would be from the left. So the limit of f of x as x approaches c from the left. That's how it's pronounced. Okay, and then just so you know, this is also called right-hand limit and left-hand limit, respectively. So this is called right-hand limit and left-hand limit. Do you remember back in number 71, I had my graphing calculator up, and I made a table of my own, and I had chosen numbers near 0. Remember that? Let's see if it's still on here. Where's my emulator? Looks like I turned it off. But my calculator had values negative 0.1, negative 0.01, negative 0.001. See, those are numbers that are on the left side of 0 and getting closer to 0. And then I also had numbers like 0.1, 0.01, and 0.001. Those would be numbers getting closer to 0, but from the right on the number line. So that's all it means. Okay? So we can try an example or two here real quick, and then bell's probably going to ring. So for my first example of the left and right hand limit, I'd like to talk about the integer function. F of x equals int x. This thing has many names. In pre-calc, your textbook had it written like this in section 2.4, and it's called the greatest integer function. Some people call it the floor function. What did you call it? The step function? Yeah, I think that's actually what the book, pre-calc book calls it. So it's been called the greatest integer function. It's been called the step function. It's been called the floor function. But basically it works like this. Any x you pick, to get the y, you're supposed to round it down to the nearest integer. For example, let's say you plug in 0. Well, that just rounds down to 0. But if you plug in 0.1, that rounds down to 0. If you plug in 0.7, that rounds down to 0. If you plug in 0.99, that rounds down to 0. If you plug in 1, that rounds down to 1, because that's the integer less than or equal to. If you put in 1.1, it's going to come out to 1. If you plug in 1.7, it's going to come out to 1. If you plug in 1.99, it's going to come out to 1. You always round down. Okay, so what happens is you get kind of a neat looking graph. And it looks like a staircase, you might remember. When I plugged in any x's between 0 and 1, I kept getting 0. It just kept happening. So that's what graphically would look like this. You plug in 0, you get 0. You plug in 0.1, you get 0. You plug in 0.7, you get 0, right? You plug in 0.99, you get 0. It's not until you actually plug in 1 that it jumps up then to be una. See? And then if you plug in 1.1, 1.7, 1.99, you just stay at 1. So it just stays constant until you hit dos. And when you hit dos, it jumps up to dos. Okay, that's my extent of my Spanish there. So that stays at 2, until you get to 3.0, and then it jumps up to 3. See? And it stays at 3, until you get to actually reach 4, and then it jumps up to 4. And this just goes on forever. So it creates this staircase. That's why it's called a step function. And each step is exactly 1 unit long by a distance formula, and then the left endpoint is closed and the right endpoint is open. But this makes for a fun problem to talk about when it comes to limits, because if you try to approach, let's say, 3 from the left, right? Let's say we actually do a problem now. Let's say someone asks you to find the limit of the integer function as x approaches 3. Let's start from the right side. If you're coming at 3 from the right, it's going to come out to 3. But if you're coming at 3 from the left, that means, 2.9, 2.99, that sort of thing, it's going to be at 2. So if you're going from the left of 3, you're on the second rung, not the third rung yet. So I'll show you just visually what I mean. If you're anywhere to the left of 3, approaching 3, you would think your destination was y equals 2, right? So you're trying to get to 3. But you wouldn't know your destination is actually empty when you get there, but your destination is 2. If you're on the right side, come along, you're on this rung, so you'd assume that your destination is y equals 3, and it is. So these two are different answers. That can happen. The assignment that I posted on Edmodo